Now, the next thing we're going to talk about, it's honestly going to take me about 2 minutes to really go over it. Then we'll start practicing it later. But what we're going to do is make the transition from here to integrals. Here's what you need to know. It's what I've already told you, but I'll reiterate it. Oops. What we're going to talk about is the definite integral. These things before, the integrals you were doing were called indefinite. They had a plus c because you weren't quite sure about the area. It was an area function, but you didn't know what the area was. Now we're going to be able to find the area. So 4.3. Wait for it. There we go. Here it is again. Last time I'll show it to you. Area. Right now you know area as this. You know area is that, right? On some interval, a to b. There's another interpretation for it. It's very, very similar to saying this. Remember how you calculated derivatives with limits? And then we found a pattern for derivatives? And you said, to heck with these limit things. This is easy. I like this, right? Derivatives are great because they don't deal with limits, which is in fact a fallacy because derivatives are all about limits. You just don't expressly calculate the limit. You understand? Same thing with an integral. An integral is all about limits, just like this. This is called a Riemann sum, or Riemann sum, however you pronounce his name incorrectly, that's what most people say. A Riemann sum is taking all those rectangles and adding them up together. That's why it's called a sum. It doesn't really matter where that point is. We typically use left, right, or midpoints, but it doesn't matter. It's an arbitrary point. What that says is that when I add up all these rectangles, I do basically the same thing going from a limit using a derivative using limits to a derivative using the shortcuts that we basically do. And that's what we can do here as well. We say, you know what? The notation here really meshes up very nicely. I've showed this to you one at a time, but now I'll show you exactly what we're going to have on top of this. When you take a limit of a sum, you basically add an infinite number of rectangles. Adding an infinite number of rectangles is denoted with this. That's an integral. Adding an infinite number of rectangles based on some function in terms of x. Where does the c sub k go? We're not talking about a specific point. We're talking about any arbitrary point that goes throughout the entire span of your x's on an infinite number of sub-intervals. And it's based on whatever variable you're talking about, dx, the width of each rectangle. If the width of each rectangle goes to 0 because n goes to infinity, that becomes that idea of a limit, limiting the x width, that's 0. Remember with our derivative, we took the x distance and we made it 0? Do you remember that? And we're taking the distance between 2 points and making it 0. And that's what we're doing here, the same exact idea. Only now we're adding together a whole bunch of little bitty rectangles instead of finding the slopes between 2 little teeny points. You get it? That's the idea. Now where's the a and the b come in? Here's where the a and the b come in. On an interval a to b, on interval a to b. This says this, basically. Of rectangles. Adding an infinite number of rectangles is denoted with this. That's an integral. Adding an infinite number of rectangles based on some function in terms of x. Where does the c sub k go? We're not talking about a specific point. We're talking about any arbitrary point that goes throughout the entire span of your x's on an infinite number of sub-intervals. And it's based on whatever variable you're talking about, dx, the width of each rectangle. If the width of each rectangle goes to 0 because n goes to infinity, that becomes that idea of a limit, limiting the x width, that's 0. Remember with our derivative, we took the x distance and we made it 0? Do you remember that? And we're taking the distance between 2 points and making it 0. And that's what we're doing here, the same exact idea. Only now we're adding together a whole bunch of little bitty rectangles instead of finding the slopes between 2 little teeny points. You get it? That's the idea. Now where's the a and the b come in? Here's where the a and the b come in. On an interval a to b, on interval a to b. This says this, basically. Add up all the rectangles with the height of f of x that have a width of a very infinitesimally small value from your starting point A to your ending point of B. Can you already do integrals? Awesome. I'm going to show you next, probably next time and the time after that, how to deal with this. It's not hard. I think you'll really enjoy it. Okay, so we are still learning about something called the definite integral. And our idea was that we can basically do, well, the idea was we had a summation, right? We took a limit of it, that was the area. We also made that into this integral and said, well, what the integral stands for is basically a limit of a sum. It's adding up all the rectangles where the partitions are, actually, you know what, for that to work, I have to make the statement, I got to qualify it a little bit. You know how we made equal partitions? Those don't have to be equal. You know how we made left endpoints and right endpoints and midpoints? They didn't have to be there. They could be any point within any type of partition that you wanted to make. Because as soon as you make the number of rectangles go to infinity, those all, no matter what the size, they all go close to 0. Does that make sense? Even though some are closer than others, doesn't matter, they're all going to 0 anyway. So it doesn't even matter if they were equal. We did that for the sake of making it easy on us. But this is what this means. It means adding up all the little rectangles, no matter what their size is, as we go the number of rectangles to infinity. So basically this is a limit of a sum, and I told you where that comes from, that's like the delta x. So this is the same thing we had before, which was called net signed area. This is net signed area. So basically this is this. And this is what you've been doing your whole, like, a lot, right? A lot. Aren't you glad I started you at, like, whatever I started you at? You did it my way, right? The way I showed you? Hope so. Sure, I did it my way.
There's a lot of effort, not a lot of results.
Now, before I tell you how to actually compute these with very little problems, because you basically already know, I'm going to show you geometrically what this means, okay? I'll give you just 3 examples on what exactly we are doing here. So when we talk about geometrically what this represents, let's talk about the integral from 1 to 4 of 2 dx. Now, firstly, can you tell me what the bounds of this integration is?
1 to 4.
Okay, so x should start at 1 and end at 4. That's where our area starts and stops. What's our function? Can you graph 2? What is it? Straight line. Very good. Straight line? Or straight line? So basically horizontal line is what you probably mean by that. And it's not this way, it's this way, yeah? So this is our 2, our y equals 2, our f of x equals 2. And we're going from 1 to 4. This, folks, is what this integral represents. It's this area right here. That's what that is. Now, for constants, that's pretty easy, right? It just says, oh, we have this horizontal line. We're going from one spot to another. Let's actually calculate the area geometrically. What's our base?
3.
Good. 1 to 4 gives you a 3. What's our height? So what's the area? Here's what I know right now. This integral is equal to 6 square units, whatever the units are. But it's an area. That's what this talks about. It says, look, you can even partition it. No matter what you do, you add up the areas of those rectangles, it's going to equal 6. You got me? That's what we're talking about. Let's talk about a couple more. Let's do this one. How about x plus 2? Could you graph x plus 2? Hope so. Hope so. Yeah. So x plus 2 says I'm going to start at 2. My slope is 1, so this is going to give me that line. And I'm going to go from -1 to 2. And this is the area that I would like to represent, is the area of this region. How do you find the area of that region? Could you do it? Geometrically, could you do it? How might you do it?
Split it up.
Probably a triangle and a rectangle is how I would do that. So maybe break this one off right here. You okay with that? Let's find the area. What's the area of this rectangle down here? How are you getting 3? So a base of 3, a height of 1. So the purple area is 3. Okay, very good. How about the area of this region? Let's do it in blue. What's the base of our triangle? What's the height? Sure. And we divide by 2. So the area is also. What's the total area? By the way, total area doesn't always equal 6, just so you know. Just so you know.
The area of everything is 6. Just put 6.
No, we did something wrong here, folks. The height is not that. 3 times. Sorry, it's not the scale, but we did something wrong. This is actually 4. What now? 3 times 3. Over 2. 9 halves. If we want to add those together, we'd get 9 halves plus 3 halves. It's going to be 15 halves. You okay with the 15 halves? Sorry about that one. Yeah, that is 3 times 3, 15 halves.
You're just proving that not all areas equal 6.
Yes, that's what I was doing. That's what I was doing. I knew something didn't add up right. But, my dot was not exactly in the right spot. How many people feel okay with our areas so far? So geometrically speaking, this is not so bad. Rectangle, rectangle with a triangle, as long as we calculate our height right, we can do that. Base times height over 2. What about something like this one? This is going to look nasty until you really think about what's going on. How about that one? What's it mean? What's it mean? What does an integral stand for?
Area under.
You guys over here asleep. Come on, integral, come on, integral. What's a definite integral? What are we doing here? Areas. That's what we're talking about. We're finding the area of whatever this function is, whatever that function is, whatever this function is. Now, I think Michael might have said it, but what is this function? Oh, it's not quite a circle. It's a half circle. Is the top or the bottom? Negative would be the bottom. Ergo, this would be that's the top of the circle. A circle is plus and minus square root of radius minus radius squared minus x squared. So this is the top half of the circle. A radius of 1. Very good. Radius of 1. That, right there. You okay with this so far? You sure? So this right here is that. Hey, tell me someone on the left-hand side of the room, what are my bounds of integration? Where am I starting and where am I stopping? Read my integral. Read my integral. See, my integral doesn't always say start where my function starts and end where my function ends. This actually says start here and there, just like we did over here. Start here and here. So basically, we have a quarter of a circle. We have a quarter of a circle with what type of a radius? How much is the radius here? Can you find the area of a circle? Area of a circle, what's the formula for area of a circle? Come on now. Pi r squared. What? Y times 1/4. This would be the whole circle. We're taking a fourth of it. So this is basically a quarter circle with a radius of 1. Which is interesting, right? Without even having to calculate these integrals, we're able to find some of those areas. We're able to do them. We didn't do anything about those integrals. But the idea is, what you're doing is finding areas. There's a geometrical approach to it. If you can do the basic geometry, you can do some of these integrals. Now, of course, do we always have basic geometry to do?
Yes.
You would like to hope so.
I was having my fingers crossed.
No, but if I give you something like x cubed, there's no basic geometry with that. Right, the x squared, there's no basic geometry with that. So we do have to have a better way. And we had the Riemann sums, or those limits of summations. We did those. That was one way. What we're going to do now is think about maybe a better way to do that, a faster way to do that. There's no better way. It's the same way. It's just there's shortcuts about that. Just like how with derivatives I gave you limits first, and then I gave you a quick and dirty way to do it. Actually, quick and clean. It was kind of nice. Pretty cool. Do you feel okay with this area approach to begin with? Can you always do it? No. But you're going to practice some of this on your homework. Be able to break up a rectangle and a triangle, some circle ideas. Now, before we do go further, I have to give you some properties, things we can and can't do with these integrals. So properties. Number one property. Okay, think through this. Think about this. Yeah, exactly. What's the area? Remember, an integral is an area. An integral is an area. What's the area?
No.
There's one,
Why?
because it's the same point.
What's the area under a single point? There's 0. The width would be 0. The height, it doesn't matter. 0 times anything is 0. So whenever your bound goes from one number to another, and it's the same number, that's going to be 0. No matter what the function is, that's 0. This is the area under a point, basically. Which is why that doesn't work. Okay, second property. This is kind of an interesting one. I get evil looks from people on this one. The interval's backwards. That's exactly right. Which means this in terms of integrals. If your integral is written backwards, like what I mean, the bounds are backwards. See how we start at b and go to a here? That would be like starting at 1 and going to 0. What that's basically saying is, if the interval is written backwards, it's talking about the area that's under the x-axis. This is this definition. It says that in order to get this written properly so that you can do the integral, this is negative a to b. Well, it's negative integral from a to b. And yeah, they really should.
It'd be a lot simpler.
But that's the definition.
We didn't even get that problem.
Do you feel okay with that so far? Now, typically, our integrals are given to us in this fashion, where we start smaller number, we end bigger number. So this, we don't use it a whole lot, but it is there for you. It's something we can do. You all right with that one? Okay. Okay, third property. Just like before, even with definite integrals, you can always pull a constant outside of your integral. So if we have c times f of x, where c is a constant, this is the same thing as c times that integral. Also, just like before, this also works with definite integrals. If you have any sort of functions in terms of x being added or subtracted, any functions whatsoever, you can split those things up by addition and subtraction. As long as you don't change your bounds of integration, basically just says, hey, integral from a to b of f of x plus g of x or f of x minus g of x, split it up. We've already done this several times with indefinite. I'm just telling you now this also works with definite integrals, which is what we're talking about here. Also, don't forget your dx. That's got to go with both of those integrals. Okay, by show of hands, how many people feel okay with the properties we've talked about so far? There's one more I got to give you. I just want to make sure you're okay on this as we are here. So area under a point, hey, it's got to be 0. This says basically, well, my integral is written backwards. It represents a function that's actually below the x-axis. We're just writing it backwards. So we can make it negative and reverse our bounds of integration. That's great. We can still pull constants outside of our integral. That's still appropriate. We can still separate integrals by addition and subtraction, not multiplication division unless we have that constant. But addition and subtraction, absolutely, just like derivatives did. Now the last one is interesting, is just for definite integrals. This doesn't work for indefinite, and you're going to see why in a second. But here's what we'll say. Now I'll give it to you with the picture first and then write it out. let's suppose that we had some function,
You really want
so easy, and there's some number between a and b, basically like some number c. Would you agree that the total area of this figure from a to b is written like that, if this is f of x? Then this is the total area of that whole figure. Would you also agree that the area of this whole figure could be written as the area of this plus the area of this? That's also a true statement. It says, if you find some number c that's between your bounds of integration, then this is the same thing as a to c. And then from where to where?
C to D.
Very good. That's another way that you can split up an integral. Find the area of just piece by piece. You can do that as well. As long as this number is between a and b, and they match right up to it. So you start at, you end at c, and then you start right again at c. Also, I don't know if I'll call this a property, but I'll list it anyway. Yeah, you actually could do it in reverse. These are not one way. I'm not going to write it twice. You need to know that if this is the case, you could write one integral out of that, for sure, absolutely. That if you have integral from a to c and then c to b, and it's the same exact function matched together, that works just fine. Okay with that? All right. Now, last up. This one, it's kind of a common sense thought, but think about this. If f of x is greater than or equal to 0, what's that mean? In terms of a graph, what's that mean? Positive. That's above or below the x-axis. So if the function is always above the x-axis, the function's always above the x-axis for every x on a certain interval, that right there says x is an element of AB. It just says x is within that, okay? So if you're confused on the notation, it says for all x's that happen to be in my interval. In English, that's what it says. For all x's that happen to be or are an element of the interval. You okay with the notation on that? If this is true for everything, you mean you plug in any x and it's always positive, it's always above the x-axis? Tell me something about the area under the curve on AB. It's got to be positive. That's what this says. If f of x is greater than or equal to 0 for all these x's, then the integral from a to b of f of x dx must also be positive or equal to 0. Does that make sense to you? Can you think through the logic on that, the critical thinking on that one? If your function's always up here, and you can actually take an area of it, then, well, the area is going to be positive because it's always above the x-axis. You don't have that net signed area, which this represents, that's actually below. You don't have anything that takes away from it. It's always above. You follow? Same thing as in reverse. I'll just state it out for you. If f of x is less than or equal to 0 for all x in AB, then the integral from a to b of f of x dx is less than or equal to 0. So it's kind of same statement. Basically. Those are really all the 6 properties we have. Area could be 0 if the numbers are exactly the same. Our bounds are the same, it's area under point, no problem. We can flip bounds of integration by making our integral negative. That's possible. We can pull out constants. We can separate by addition, subtraction, definitely not multiplication. We can also break up an integral if it is to our benefit, or put one together if it's to our benefit, provided our functions are the same, and there's a number between there that we can split up. That's okay. Also, this is just kind of a statement, but it is truth. If the function's always above the x-axis, area's gonna be positive. If the function's always below the x-axis, the area's gonna be negative. That's the idea. How many people feel okay with our properties just fine? Cool. Let's try one more geometrically, and then I will go on into how to actually calculate these definite integrals. Trust me, it's not hard. All right, if you know how to do indefinite integrals, you're almost set. Just one more thing. So last little example here. Let's use some of these properties and what we know about the area approach to these integrals and find the area of this thing. There we go. Now that looks kind of nasty. In fact, you probably wouldn't even be able to take the integral of that if you didn't think about the area here. Because when you look at that, you're thinking, well, substitution, can I even do that with the definite integral, first of all? Because we haven't talked about it. Is it even possible? Will be. But secondly, even if I did a substitution, the substitution doesn't really work out that well for us, at least not exactly. So that might not even work. So we have to kind of think about the geometry in this particular part of it. Using some of these properties, tell me something I could do. Definitely separate. So from 0 to 1 of 4dx minus, tell me something else I could do on the second part of it. After I write this way, I'll write every step for you. Yeah, absolutely. I can pull that constant 2 out in front of my integral. You okay with that so far? Now at this point, well, we got some things we've talked about already today. Tell me, can you find that? Yeah, that's pretty easy actually. That's going to be, and I'll draw it in a second, that's just going to be a horizontal line at 4 from 0 to 1. Find that area. This one, what is that? That's a half circle, and I'm going from 0 to 1. That's a, we've done that problem already today. So what this says is, four, 0 to 1. What this one says is a quarter of a circle. So basically what our integral comes down to, our area is, what's this whole area? 4. Minus 2 times, don't forget the 2. This was pi over, what was it, pi over 4? We got this area minus 2 times this area. So 4 minus 2 times pi over 4. If we simplify just a little bit, area is 4 minus pi over 2. If you really want to find the common denominator and do that, I think you'd get 8 minus pi over 2 if you really want. It doesn't do you any good to do that, but you could if you want to. Do you feel okay with breaking these things up and using some geometry? So in this section, that's what you're going to do. I haven't taught you how to directly attack a definite integral yet. I'm going to do that right now. This is kind of a roundabout approach. We say, let's think about the geometry. Let's draw a picture of it. Let's use our geometrical approach to find area, and that's what this represents. Would you like to see how to hammer out a definite integral just right on? Yeah, I was hoping so. This is the good part. You guys ready for the good stuff? This is the good stuff. Woo. You know why it's good stuff? It's got cool words in it, man. Words like fundamental and theorem and calculus. Oh. We're going to talk about the fundamental theorem of calculus. Oh. That's right.
I'd really like to see what your weekend consists of. It's like in front of the mirror doing all this
Oh.
stuff.
When I go to the gym to get my pump out, I just go, derivative! That's it. No, that's not true.
Maybe that kid that you picked up.
I get it.
Whole semester, they just like gave you the other calculus.
Yeah, basically. Here's what you know so far. You know that this is an area. You also know how to calculate indefinite integrals. You know how to calculate them like this. That this was capital F of x plus c. Remember the plus c part, all doing that? We know how to do integrals. We've done that already. Here's what this represents though. What this says is, okay, an integral represents an area. This is the antiderivative, but what do we do with that plus c? Let's talk about that for right now, and then we'll have a really good picture of what's going on. So here's our, I'll use the same graph I have over there. Here's our graph, and this is f of x. We're looking for the area. What we want to do is find the area from A to B. That's the goal, without using our Riemann sums or the summation notation. We don't want to do that. We want to really just think of this as an integral because we know an integral geometrically represents the area. So how can we go from this picture and this thing and tie it all together? What we want is the area from A to B. Here's how we're going to think of it. We're going to think of it as, well, how about this? Could you find the distance from A to B? How would you do it? You would do B minus A. If this was 10 and that was 3, you'd do 10 minus 3, right? We're going to do basically the same thing. We're going to say, let's take the area up to B minus the area up to A. Would that make sense to you? We'll take all of this area minus off all of this area. No matter where you start, that would work for you. Would you agree? We'll take all the area from left to right, all the area, no matter where we start, up to B, and subtract off all the area up to A, and that would leave us with this little bit. How many will buy into that, feel okay with it? That's exactly what we're going to do. So we'll take the area up to B,
Starting from infinity?
starting from wherever you want. It does not matter, as long as you start the same.
One for both. Yeah. Okay. Point A.
Say what?
Can you just make your starting point A, which says you didn't figure out the area of B and you subtract 0?
Well, I had to give you something that this makes sense, right? And the way to do that, we are going to start at A and go to B, but find the actual, you can see why we have this next piece in there. Right now, if I give it to you, you'll probably follow it, but I want you to understand the concept of why we have a subtraction in this at all. Okay, and we're going to have one right now. So let's think of it. So, the area is, this is not changing. The area is this. What we're going to do is take the area up to B minus the area up to A. Now here's what you have to realize. What we're doing here is calculating the area function. Do you remember me introducing that to you a long time ago? That this indefinite integral actually is an area function. It was a family of curves. We just know which one it was. Well, if we have that family of curves and we're going to an actual point that says this is where you're going, you're stopping here, that solidifies it for you. It's no longer indefinite, it's definite. You're starting at one point, you're stopping at another point. So this right here, that's an area function, and we actually have something to plug into it. We have the point, well, where are we stopping? The area up to B you find the area by plugging in B. The area up to A, you find the area by plugging in A. So the area from A to B is the area up to B. The area up to B. That would include wherever your starting point is for area, that would include everything up to the point B. Everything above the x-axis to the point B, you got me? And then we'd subtract off this point A. Now, really what we'd consider is starting from 0. That way we're not being silly about it and going way too far. We'd say, let's just go from 0, okay? You'd have this area minus this area, it'd give you what's remaining. The area up to B, plug in B. The area up to A, plug in A. That's how you do a definite interval. You find the antiderivative and you plug in your bounds. It's actually that easy. Not bad? Not bad. No, come on, now there's one question out there. What's the question? Come on, do you see it?
What do you do with C?
Oh, good. Do you see it? Where's the C? By the way, this right here, this statement is the fundamental theorem of calculus part 2. I'll give you part 1 later. Fundamental theorem of calculus
F.
part 2. What happens to the C? Oh dear, why don't we have a C? Why not?
Now you know definitely what you're going to.
Well, you do know definitely, so we shouldn't have a C. But when you think about it, remember when we're finding out this right here? This is a family of curves, right? How are you supposed to know where it's at? Wouldn't a curve way up here have a different area than one right here? Clearly, the height would be different. So why does this even work? Well, think about this for a second. What about the C? What about C? Suppose you considered it. By the way that you write this, I should actually give it to you this way. One more thing, this is also written. As f of x. That's an evaluation symbol from A to B. That's how you can write that. And we're going to be practicing that as well. It says the same thing, okay? This and this is the same. How you do this is you plug in B and you subtract off A. You plugged in B to your antiderivative and you subtracted off f of A. Are you guys okay with the notation? So when you see that line right there, it's like half a bracket, goes from A to B, that's what that means. So if this equals this, and this equals this, let's suppose that we actually included the C. Now, some of you might be wondering, well, when you think about it, you might be wondering, why don't we have a C1 and a C2? Say it again.
They're the same constant.
Why are they the same constant? How do we know that for sure? He's right. Why? Say it louder. They're from the same function. If you're integrating that same function, you're not switching functions on me, are you? Integrating the same thing. Then whatever C you get is your C. No matter what you're plugging in, that's going to be the same function itself. Does that make sense? So wherever you're at, that's the same function. If we integrated one time, look what's going to happen. If you have f of b plus c, it's not c1, it's just c. F of a plus c is not c2, it's just c. What's going to happen to my c's? Wherever your c is, that height difference will be eliminated. It drops out of your equation, as your book likes to call it. The c's are gone. So remember, the plus c, that's just the height, right? Height of your function. Even if it's way up here, same type of function, just way up there. But both of them would be way up there. The f of b plus c, f of a plus c, we're subtracting out that plus c part. The plus c's will be eliminated from your equation. And that's how we get what we get. So the c is gone, drops out, so we don't write it for our definite integrals. Indefinite, absolutely. But definite, we should end with a number, end with an area, because this thing is an area. By a show of hands, how many people feel okay with what we talked about so far today? Would you like to try a couple examples? You're going to really like these, by the way. Are you ready to really like something
Yes.
in this class?
It's been a while.
Oh.
After that this weekend. Great, now we're over fail.
Yep. You're sunk now.
Welcome to that early transcendentalism.
Exactly. Okay, so an integral from 1 to 5 of x dx. This is an area, which means we should end with a number. It's actually a definite integral. Why is it a definite integral and not an indefinite integral?
Constraints.
Right there, there are bounds of integration. We actually have numbers. We should end with an area. Now, can you integrate x dx?
Yeah.
Easily, yeah, we already did that. No need for limits, no need for any of that stuff that you spent your whole life doing just now, okay? It's doable, you did it, right? But this is a shortcut, not a shortcut, I guess it's a shortcut to doing it. What is the integral of x, please? Where are we integrating from? Where do we start our area, where do we stop our area? 1 to 5. Why don't we have a plus c here?
Because we have low.
Even if it fell out, even if we did, it's gone because you can subtract it off anyway. It's the same plus c. 1 to 5. Here's how you show your work. You do this step first. You show me what your integral is. You show me where you are plugging in numbers from. You plug in the top one first, subtract, then plug in the bottom. This would be 5 squared over 2 minus 1 squared over 2 is how you show that. Do you see where the 5 and the 1 are coming from? So we're going to get 25 halves minus 1 half. How much is that? 12. Yeah, 24 halves is 12. Is that quicker than a Riemann sum? All the stuff you've been doing, left endpoints?
Yeah.
What is 12? What's 12?
Area.
Exactly right. Area under that curve, which is just a diagonal line, from 1 to 5.
Yeah. Thanks.
You're welcome. Well, the other stuff is good to know. It shows you where it's coming from. It shows you why you're doing it. It shows you how you do it, and you make sure you know what all this stuff means, right? If I just gave you that, you could do it, but you'd have no way, you would not understand it. We did the limits of the sums so you would understand why you do this, how you do this. Now, we needed something else, though, because when we get to things like this, a Riemann sum doesn't work all that nice for that. Maybe you'll do an integral with that. So this is also an area. It's an area from 0 to pi over 2 of cosine x. That's your cosine curve. Now, the integral of cosine x, you got to be able to get these right, otherwise your areas are going to be wrong. You'd show an area above the x-axis when it's below, or below when it's actually above. What is the integral of cosine x, please? Do you need to memorize that?
Yes.
Yep. And where are we going?
0.
Which one do we plug in first, the pi over 2 or the 0? Which one? The pi over 2. Otherwise, you'd have negative, which is, by the way, if you notice that, when your bounds are reversed, notice how you're subtracting off the wrong thing? That would switch your sign of your area, right? That's why the property I gave you where you can switch your bounds and it switches the sign of your integral, that's why that comes about. So here you'd have sine pi over 2 minus sine of 0. All right, come on now, people. I know you love some trig functions. Throw it at me. 1. Which one's 1? 1 minus
0
equals
1.
your area is 1. That's weird. Oh my gosh, have you thought of this, what this is? Do you understand what this is?
Yeah.
What's the picture?
Yeah. And you're just picking one little spot.
Starts here, goes like that. You're there. Right? Hope so.
That's a
That's cosine starts there.
function cosine.
Cosine. Cosine goes to, oh, I'll have to erase it to draw a better picture. Did you have questions on that?
Nope, I'm good.
Watch the video. On what? You just found, yeah, don't draw these first, draw your curve first. Shoot, come on now. So a teacher in master's degree. Boom. Yeah, that's your area that you just found, that's equal to 1. Isn't that very interesting? That's interesting. It really is interesting.
Which means the next section would be
Hopefully negative 1.
and then it'd be like positive, so on and so forth.
Positive 1, negative 1, negative 1, positive 1.
Okay. And then it'd be positive 1, so it all
Add it all up?
0.
Yes.
Okay. Is that just
Which means the area of a circle is 0. Did you catch that? Wouldn't it be if you did an integral?
Yeah.
Yeah, because you have the area above and the area below would match up. Because we're talking about net signed area right now. We haven't made it to total area, which is what we'll do in just a little while. We haven't made it there yet. Total area would change the area below the x-axis into something above the x-axis so you can actually add it together. We'll talk about that in just a bit. For right now, we'll do a couple more examples just to really illustrate this stuff, and then we'll go till the next class.
Now, always adding up to 0. Is that still true for also tangent?
No, tangent has undefined points. You can't go further. If you think about tangent,
Yeah.
tangent does this. Also one that would probably be kind of hard with Riemann sum and those limits, okay? Not one that's great. However, can we do integrals with it? Sure, sure. You tell me what you do first.
Can't split that.
Why can't you split that up?
Okay.
Ah, darn it.
I get rid of your square root, turn it into x over 1/2.
X to the 1/2.
Then I would.
That'd be a good idea.
Then I'd combine the two. And then you can do your standard integration.
Sure. Don't jump to something super hard right away. Don't jump to a substitution. I haven't even showed you that for this yet, right? So that's off the table right now. Don't jump to that stuff. See if you can do it easily. Make sure you maybe change a root or two. Substitutions often work when you have, well, trig functions is a good indication for that you should probably try. Or if you have parentheses, that's a really good indication you should probably try. And it won't distribute nicely. That's a very good indication you should probably try. So, x to the 1/2, yeah, I'll bind to that. dx, I like that. And combine them. X to the how much if we combine those?
1.
You add, right?
You add, so it's 5/2.
X to the 5/2, yes? Can you take an integral of x to the 5/2? Very easily. This would be x to the 7/2 over 7/2. Over the same exact variable. No, I'm sorry, exponent. Exponent up top, exponent on the bottom. No problem. Make it a little bit prettier here. We're going to have 2x to the 7/2 over 7. And then we get to evaluate from 4 to 9. We plug in the 9 first. I've actually given you some nice numbers. Do you know how to do 7/2 without a calculator? Or to make it quicker on a calculator? This is power over root, right? Oh geez, I hope so. Do you remember that? Power over root? So you can take either one, whatever you want first. I would take a square root of 9. Square root of 9 is 3 to the 7th. That's what you plug in your calculator. I can't do that in my head. That's a pretty big number. 3 to the 7th is huge. So this is 2 times, someone tell me what 9 to the 7/2 is, or 3 to the 7th. How much? Minus. This is the square root of 4 is 2. Then you do 2 to the 7th. Which is 2 to the 7th. Are you okay on getting those numbers out, ladies and gentlemen? 2 times 2,187 is what?
43.74.
This should be 256. Someone give me, since we already have a common denominator, someone give me 4,374 minus 256, please.
4118.
Does that simplify at all? That's not divisible by 7? Then you leave it. You could do a decimal if you really wanted to. Let's make sure before we end this that our math is correct. Can I get a double check on 2187?
Yeah,
You got that as well?
that's,
Can I get a double check on the 128?
same thing.
Same thing here as well? All right, how many people feel okay with what we talked about so far? Awesome, we'll try a couple more examples. We're almost done with our definite integrals.
That is so much.
All right, well, what do you say we continue some examples? Here we got the integral from 0 to pi over 3 of secant squared x dx. Now, we don't have any substitution for definite integrals yet. I'm going to show you something about that in a little bit. So right now, everything basically has to fit our integration table. What we learned last time was that when we do an integral like this, a definite integral, we found out firstly how to do it, and secondly, that's exactly like finding the area with the Riemann sum, or the sum of those partitions, which is very nice, very, very nice. So let's go ahead and let's take the integral of secant squared x dx. Do you all remember the integral of secant squared x dx? Tangent. Tangent squared or just tangent? Good. So here's how you write that. You'd say, okay, I know this is tan x plus c or not.
No.
If it has bounds, no, because you're going to find an actual area. Because what you're going to do right now is you're going to be subtracting f of b minus f of a, and if those did include c, it'd be the same c that would drop out of your equation anyway. So no, we don't have a plus c on this. What you do is you have this first, and then you throw up, sorry, that's it when you get home for your homework. You put up the integration, or sorry, the evaluation symbol. You go, okay, I'm evaluating from 0 to pi over 3. So therefore, you show me what the integral is, you show me your bounds of integration, your bounds of evaluation, and then you plug them in. Which one do you plug in first, 0 or the pi over 3? Okay. So what this says is tangent of pi over 3 minus tangent of 0. Well, that's not too painful. How much is tan pi over 3? Don't leave me hanging. Awesome. 1.73, like my calculator says. Yeah, okay, very good. Learn a unit circle. Root 3. Root 3 over 2 divided by 1/2. Reciprocate, multiply, you get root 3. That's because it's sine over cosine. You need to know that. Okay, anyway, so we have our integral, the area underneath the curve of secant squared between 0 and pi over 3 is, we got it, square root of 3. It's interesting, right? It's kind of weird that we're able to find those areas so nice and neatly. Are you ready to try a couple more of these things? Yes, no?
Yes.
Did that make sense to you? Besides the square root of 3, which you all just kind of screwed up right now? All right.
You have so much faith in this one.
Hey, you're the one who screwed up, not me. Okay, explain to me something about this problem.
You have to invert it and change it from negative integer.
Okay, very good. Explain why. What's wrong with this problem?
It's backwards, the bounds are backwards.
It is. It should go from smaller to larger bounds. In fact, you know what? If you did it like this, if you did, you would get, I believe you get the right answer, actually. If you try it right now, you'll get the right answer. But that proves the statement that we had before, that this is going to be negative. So for instance, if you did this, you'd get x to the 4th over 4, right? No plus c. But if you evaluate it from 4 to 0, like it says, you'd have 0 to the 4th over 4 minus 4 to the 4th over 4. And what that would end up being is negative 4 to the 4th over 4. So 4 cubed, negative 64.
So
If I've done my math correct. Did I do my math correct?
Yeah.
Yeah. Now let's check to see if we get the right answer the other way as well. We also knew from a property that if I reverse this and go 0 to 4, that becomes a negative. Well, let's see. That would be negative x to the 4th over 4. That would be negative. You need brackets there because you're going to have a sign in the middle of that. And that's evaluated from 0 to 4. 4 to the 4th over 4 minus 0 to the 4th over 4. And that would give you negative 64. Negative 64. Which by example kind of proves that that was true, that I can reverse my bounds, and that makes me change my sign. So just by an example, we see that that is true. But notice how you do actually get the same exact answer either way. That's because it is true. It has to be. What it represents, though, is kind of awkward, because this looks like it's an area above the x-axis, when in fact it's not. This is just read wrongly, incorrectly. So the correct way to do this problem would be to write the bounds in the appropriate order with the negative out in front of it, and that would give you negative 64. Either way, but this is kind of showing you, okay, this is an area underneath the x-axis, not above it. How many will feel okay with that one? Okay. Oh, lost it. Okay, we could bring the x squared to the top. Now what?
There we go.
There we go.
Could figure out how to say it, but.
Okay, all right. You'd have negative 1 over 1 minus negative 1 over negative 1. Yes, no? Hopefully, if I did that right, make sure my signs are correct. I'm looking at that as negative 1 over 1 minus negative 1 over negative 1. That's negative 1 minus 1. Negative 2? You get an answer. You do. But now, think about the answer. Well, you can have a negative area. It would mean it's underneath the x-axis.
Oh.
That'd be okay. Think about the function then. Graph it on your graphing calculator if you can't think of the function.
It's a domain error,
Why?
because it's negative.
No, not because it's negative. Think about the function. What's the function do? I don't want to draw it in crayon for you. Think about what the function actually does. We have done so much in this class for you not to know this. Say what? Where does it have an asymptote? Okay, it does have those. That's okay though, because I'm between negative 1 and 1. Between that. Draw the graph if you have to. Draw it. should know the shape of that graph. You really should. Okay, you're gonna make me do it. You're gonna make me, oh my gosh. Plug in 0.
No, it has, yeah, it has to.
Plug in 0. Plug in 0. Can you plug in 0? Why not? So what's it tell you at x equals 0? What do you have? Look at your bounds. Where do they start?
On each side.
Okay, so are you adding up areas that actually are undefined at 0?
Yeah.
So since you're making rectangles, one of those rectangles is going to infinity. Do you see it? There's probably infinitely many of them are going to infinity because when you go that close, you're going to infinitely many anyway. So can you actually add the area? Even though you can do the work, that doesn't exist. There's a theorem in calculus. I don't think I get to it, but basically it says that if you're not bounded somewhere, if you're not bounded, you can't add up those areas. So if it goes on forever in one direction, right? You can't do it. So you have to have that. Here we have an asymptote going to infinity. We're not bounded in any way, shape, or form. Therefore, that area cannot exist. Or it does exist, but you can't find it using the methods that we use. There could be something else. I'm not sure if they have a way to do that, to be honest with you right now. But I, for what we know, that doesn't work. It's not -2. If you think about 1 over x squared, that's positive anyway, isn't it?
Yeah.
And if I did my signs wrong, it would come out to 0. I don't think I did I do my signs wrong?
No.
Hope not, I did it real quick. But if you did, it would just come out to 0 anyway, which you know there's an area. It goes like this. It's a positive area, so that it makes nonsense. And it's because there's a domain issue. You had it right. It's not the negative. It's the fact that we start here, we end there, and there's a problem between them. That would be the problem. Do you get it? There's a problem at 0. 0 is between -1 and 1. You have to be at least bounded between there. Typically, you have to be continuous and bounded, and that would make it work. Yeah.
Even if our bounds were a little bit wider, it still would be undefined since that you can't measure at x equals 0.
What I mean by bounded isn't this way. I mean this way. You have to have this.
Upper limit.
Here's a curve between these 2 points. It's got to have a low point and a high point, which means you can come up with something here and come something there that's between. Actually, really, it's just, if you're just talking about the x-axis is only above, it just has to be bounded above. It doesn't go anywhere. If it was below the x-axis, it'd be bounded below. So this one's really irrelevant when you're talking about the x-axis. That one doesn't matter. When you find an area here, it's got to at least be bounded above. When you do something like this, hopefully you see the problem. Do you see the problem? How are you supposed to add that area up? That goes to infinity. You can't do that. It doesn't. I don't know what the area is. I don't know if you can. If you can say infinite area, I would assume so because it's going to infinity. But you can't calculate it like this, How many people understood that? Where the problem is? What's the problem again? Explain it to me again. What's the problem? Domain issue. Why a domain issue? Someone else. Domain issue. Why?
Because it's undefined.
Where? At 0. And why is 0 important?
Because it's within
Aha,
constraints.
aha. It's actually in our interval. If I had done this, would there be a problem?
No.
Not at all. But if I cross over that undefined point where we have a domain issue and going to infinity, that's an issue for us. We can't do that. Now, is it kind of clear for you? All right. You guys had it. Come on, you should have known that. You should have right at that. You should know that this picture looks like this, too. Like that. Just by thinking about asymptotes, you should know that. Asymptote going to infinity is like this. Asymptote in the middle goes like this. Sign analysis says they're both positive. Plugging in positive is positive. Plugging in negative is positive. It goes like that. You should know that. Anyway, this, none of that works.
So we just put undefined for.
Well, this one you would do.
Oh yeah, the new one we would do, but the original problem would be try undefined or.
You would explain to me that there's a domain issue and that since our bounds are going from -1 and cross over somewhere where we have a vertical asymptote, therefore in no way can find the area of that curve between those 2 points. Okay, now let me show you one more thing that we can do. Are you ready for it? Were there any more questions on that one? That was a good one, huh? Even though, because it looks like you can do it, and you do it, and you go, I win, -2. But you don't think about what the function actually is, it burns you up. You don't want to do that. By the way, don't assume that all of them are going to be like that on the test. So if all of you go, oh yeah, it's got a domain issue, I can't do it, you're probably mistaken. I'm not going to give you 20 integrals that you can't do, okay?
You might get one of those 20 right.
Yeah, maybe one, maybe one.
Wishful thinking.
I always find that funny. I tell you one thing and you always assume it's that thing. Oops. Oh, you know what? I could show you one more thing on this so that you would actually see it as well. If you should know, going back up here, you should know that because of our property that we had, yeah, maybe one, maybe one. And plain and David. Anyway, well, this one you would do.
Oh, yeah, the new one we would do, but the original problem would be right undefined or.
You would explain to me that there's a domain issue and that since our bounds are going from -1 and cross over somewhere where we have a vertical asymptote, therefore in no way can find the area of that curve between those 2 points. Okay, now let me show you one more thing that we can do. Are you ready for it? Were there any more questions on that one? That's a good one, huh? Even though, because it looks like you can do it, and you do it, and you go, I win, -2. But you don't think about what the function actually is, it burns you up. You don't want to do that. By the way, don't assume that all of them are going to be like that on the test. So if all of you go, oh yeah, it's got a domain issue, I can't do it, you're probably mistaken. I'm not going to give you 20 integrals that you can't do, okay?
You might get one of those 20 right.
Yeah, maybe one, maybe one.
Wishful thinking.
I always find that funny. I tell you one thing and you always assume it's that thing. Oops. Oh, you know what? I could show you one more thing on this so that you would actually see it as well. If you should know, going back up here, you should know that because of our property that we had, that should be true, right? Shouldn't it? But now when you think of that, you go, oh, there's a problem there. You see the problem there? Now it's 0, the ending bounds there. You couldn't even, if you tried to do the integral there, you couldn't even plug it in. You'd have undefined and undefined, and that would show it to you right there. Okay, so it's tricksome when I put it like this, but when you see it like that, you go, oh yeah, that's more clear. That's more. Now, how about this one? Oh my gosh, a piecewise function. Can you do it with a piecewise function? Of course you can. It's actually not even that hard. What you have to do, though, is realize what this question is asking you. This question says, I want the integral from 0 to 6 of f of x, where f of x is defined as x cubed when x is bigger than or less than 2. 5x minus 1 when x is bigger than or equal to 2. So, can you break up this integral in a very similar way I did up here so that you can make maybe 2 different integrals?
Yeah.
Well, let's do that. Where's our first integral going to start? Let's do this. 0, very good. And where's it go?
2.
Yeah, because that's our separating point over there, 2. What function is defined between 0 and 2, the top one or the bottom one? Good, the x cubed, very good. Plus, because we know, using the property actually defined up here again for you, we can separate an integral into 2 different integrals by matching up the bounds. 0 to 2 and then 2 to 6. Of which other?
5x minus 1.
If some people might have a question, well, does it matter that this one's actually less than 2 and this one's greater than or equal to 2? No, not really. We have such small rectangles, it doesn't really matter. They're all going to mash together anyway, so no, not really.
If you had, say that it wasn't greater than or equal to 2, then if it would say it was just greater than, it would matter, correct? Because then you'd have a gap right there.
No, it'd still do it. Although, wait, did you say that this one changed?
No, the one below it,
Oh,
say that
that
equal.
didn't have it, then you'd have an undefined point. Yeah, I'll say it this way, the area of one point doesn't even exist anyway. So you could technically do it with 2 different integrals because the area of that one point doesn't matter. It's 1 point. The width of 1 point is, you can't do it. There is no width between 1 point. It's a point is that which has no breadth, which means it does not have a width. No matter what the height is, the area would be 0 of that single point. However, this wouldn't make sense from 0 to 6. This one couldn't be given to you like that because this says continuously from 0 to 6. And so that really wouldn't make sense. Does that make sense? I couldn't do that to you because you wouldn't have the ability to break it up because to break it up it does have to be continuous. I think I gave that to you. I don't know if I stated it word for word the way the book does, but in order for that property to work, the ability to split up the integral, it's got to be continuous. That's another reason why this one would fail. That's not continuous. Do you get that? So you couldn't even split up to begin with. It's got to be there. It's got to all be there. You got to have the ability to break it up. That's the only way this works. Otherwise, you are missing points, like you pointed out. That's a good point. Great question. I talked through that pretty quickly. Are there any questions about what I just said? Were you able to follow it? Yes.
So, same thing if it was, if the bottom function is 5x minus 2 or something, and there's a jump, then you wouldn't be able to do it either? Or
If they didn't actually match, oh, that's a good question. You mean if there's an actual gap, like if we plug in 2 and it doesn't,
right, like they're not the same for both functions.
yeah, they're not in this case.
Oh, you're right.
Yeah, they're not in that case. No, it doesn't matter, just it means that you're defined for every point from, in this case, from 0 to 6, that you have something for every one of those points.
Okay.
That's the ability to break that up. Now, in practicality, does that, if you add those areas, or you add, what was it here? If you add those areas, it's going to be the same. You just can't do this if you don't have that. That's the point. Does that make sense? You just can't do it. Legally speaking, you can't do it.
Theoretically, it would make no difference, so.
Theoretically, it does make a difference. That you cannot
practicality,
actually do
yeah.
it. Practically, this area plus this area will equal this area. Yes. Sorry.
Right now.
This area plus this area plus this area. I should do it this way. This area. Plus this area, even like that, will equal that area because the area under a point is 0, but you can't do this unless you have this. That's the point. Dang. Good questions. You're making me work for my money today. That's why they pay me the big bucks. You know that, right? Explain all this junk to you. I don't get paid big bucks. The Audi I drive is 01, so. Hey, the integrals aren't actually that hard. It's plugging the numbers and getting that right, huh? That's the biggest problem in math is the small stuff. My gosh, don't forget any signs, don't lose anything. Keep track of all your numbers, get that stuff right.
Why is it X?
Oh, four, sorry.
That was, yeah.
New math.
Government policy.
Did y'all get your integrals correct? You got x to the fourth over 4 from 0 to 2. You got 5x squared over 2 minus x. You didn't forget about the minus 1, right? From 2 to 6. Did you get that far? Okay. Now we plug the numbers in. I don't know if I should count on you guys on that one.
Just give us some more trade, we'll get that.
Right. You know, you really need some brackets and parentheses on this thing because you got stuff going all over the place, especially when you have those multiple terms being added or subtracted. This one's pretty easy. This one you just plug in the 2 and you plug in the 0, and that's very straightforward. You get 2 to the 4th over 4 minus 0 over 4. This next one, you got some things going on. Notice how you have to plug in the 6. That's giving you the 5 times 6 squared over 2 minus 6. Then you plug in the 2, but you're subtracting. Remember, it's f of b minus f of a. The whole thing. Do you see why the parentheses are important here? Okay. If you wanted to distribute, you distribute, and that sign would change. Now, typically, order operations say you add all that up together before you subtract anyway, but it's important that you know that. So we're plugging in the 2. We got all that down. You want to help me with the math? That should be what, 4?
Yeah.
4 plus, so that's 4.
84.
36,
It's 90.
90?
90 minus 6,
84, okay, so that's 84. Eight? Minus 8, right? Looking like 80 to me. Did you get 80? Cool. How many people were able to find the 80? Did you feel okay with it? If you weren't able to actually do it on your own, were you okay with it? Now, what's it represent? What did we just find? The area of what?
A piece.
Yeah, of this, when it's defined this way between 0 and 6, you found the area under that curve. Or actually, the area, the net signed area. If this thing went below the x-axis, I can't see that it does, but if it did go below the x-axis, then we would actually have the area that takes the difference between the area above and the area below. That would be net signed area. Do you feel okay with this example? Do you have any other questions?
So whenever we have multiple terms in one, we just take the first one, put in for all the x's, solve, and then take the bottom
Absolutely.
one.
What this says to do is you plug in the 6 the whole way through, you figure it out. That's the area from 0 to 6
Right.
of this function. Then you subtract from 0 to 2, and that's what that's going to give you. Okay.
And so no matter how many terms we would have.
Plug them all in, then subtract, and then plug them all in. And that's what you do. You got to plug them into everything. Yeah, and for this instance, your x becomes 6 everywhere you see x. For this instance, your x becomes 2 wherever you see x, and then you subtract, and that's what this meant. F of b minus f of a. That's what that meant. You take your b, you plug it in. Take your a, you plug it in, then you subtract it. Now, what we've been talking about this entire time is something called net signed area. I gave you net signed area before.